Morning, everyone. I welcome everyone for the last day. It is day 10 of our GAM workshop. So, the first session, forenoon session, we have a tutorial 13. After the break in the forenoon, we have a tutorial 14 that we are going to take it to our department for demonstration of the solar photovoltaic, how the renewable energy can be brought into the for the ammonia generation. Then followed by, we are going to demonstrate the microwave pyrolysis and thermal gasification system. If possible, we can also give demo on electrical panels. So this is most important part of any implementation of the project. Any new projects, government or the institute or the, I can say the startup, we need to plan for any new kind of project. The LCA, what is very, very important. We're going to talk about the social, economic, and environmental thing. And when you are focusing only on environmental perspective, it's called life cycle analysis. If you are focusing on economic perspective, it's called LCC, life cycle cost. Then if you are talking about social perspective, and I can say it's called social life cycle analysis. So in terms of this life cycle analysis, what we are going to see the different inputs and different outputs comes out from the particular process or particular industry. Here, majorly I can say for environmental perspective, water, energy, materials, and emissions are considered as the input and output. Inputs are water, how much the water is consumed, how much the energy is consumed, how much the material is consumed for bringing the system. Then in terms of emissions also we need to think about. And if you want to bring any new project, social responsibility is also there. So we should think about the people living in that place. So what may be the impact of the social impact as well as the benefits for the people, those people. Then similarly, in terms of economic, you are going to invest so much of money, how much the revenue you are going to, okay, say get. Maybe after some time, maybe the payback period of maybe after some time, you are expecting the revenue, right? So you are investing something, you are in need of revenue also. So in the life cycle, slide. Life cycle thinking, yeah. So any new analysis or any new project, first need to think that. So what is the use of that project? Okay. So the life cycle thinking divided into three components: environmental, economic, and social. Environmental talks about LCA, economics talks about LCC, then social talks about social LCA. So in that there are inputs for environmental, there are inputs for economic, input for social. Similarly, you are expecting the output from the environmental perspective of analysis, then revenues in terms of output in terms of economic, here the benefits in terms of social. The concept of life cycle thinking refers to the complete sustainability of assessment of a technology, product, system, comprising the analytical impacts which occur across the supply chains when providing a product. So we are this workshop really focusing on replacing the Haber-Bosch method to produce ammonia into renewable based. So if you are replacing the Haber-Bosch by going for renewable based, what may be the environmental impact, what may be the economical impact, what may be the social impact, that is nothing but a life cycle thinking. Okay. You can post it.
Life cycle.
Okay. So continuation of the life cycle thinking, and here we are this workshop we are speaking about, I can say, the Haber-Bosch the replacement of hamper bolt is a different, I can say, method we have discussed. So the ultimate aim in doing LCA for this kind of, I can say, the process hammer bolt is to replace the hammer bolt with the new methods. So in that case, you need to think about replacing the hammer bolts with the renewable waste. So what are on the social, what are on the economic, what are on the environmental perspective for development of, I can say, bringing the new concept. So we are interested in sustainable ammonia. So ultimately, the life cycle thinking is we need to produce ammonia in sustainable manner. So by bringing the three categories of economic, I can say environmental as well as the social, you need to do some kind of analysis. So the product life cycle analysis, you can also do it. So you can take different inputs, raw material, transportation, processing, right? Then the end life of this one, the retail and use. So every process you can able to do the, I can say, life cycle analysis. So raw material extraction, manufacturing and processing, transportation, usage and retail. So if you are claiming that I'm going to produce ammonia from the, I can say, from the water, then you need to prove that your ammonia generation, we are not going to bother about it initially, but the way in which you are producing ammonia, right? How is going to, I can say, in terms of social perspective, in terms of economical perspective, in terms of environmental perspective, how this process is going to be superior than the hammer portion. So that you need to prove that. Then you can refine it later. Automatically, I can say after maybe because you cannot replace hammer portion of, I can say, the way of ammonia generation. But as the government of every government is putting a lot of stringent emissions, and the per ton of ammonia, how much the cost you are going to spend. So everything matters. So in that case, you cannot do, I can say, experimental study to come up with a solution. You need to depend on some kind of tool to find out the, I can say, life cycle of the particular system. Otherwise, analysis for in terms of economical, environmental, as well as the social. Okay, there are 4 phases of life cycle assessment. First one, goal and scope. What is the goal? What is the scope of it doing that? It is necessary to do that, to move to the renewable energy from the conventional way of, I can say, producing hydrogen from the methane, natural gas, and converting the hydrogen into ammonia during hammer bosch. It is a proven technology. Why you need a, I can say, renewable based way of producing ammonia? You must have a goal and scope. Right? When you want to suggest something to the customer, you need to have concrete goal. What for you are going to bring the technology. Then what is the life cycle inventory? Suppose how much you are providing, right? You can think about the plastic, right? So the raw material is maybe I can say polymer is entering. But what is the outcome of that particular I can say the plastic? So it is not going to be again, I can say, consumed. Must go to input again. So we are not utilizing it in plastic properly. The life cycle inventory is very, very important. That's called circular economy. So how much quantity you are consuming, either you can able to reuse it back for the same process you are going to bring it for getting the product. So the life cycle inventory also very, very important. Then you need to do the impact assessment. Economic, environmental, and social impact analysis and all you do. Then finally, you need to interpret it by combining 1, 2, 3. You need to interpret it. So whether your technology, what you are bringing for replacing the conventional method, is going to be acceptable level or not. Okay. So you can define the goal and scope. Inventory analysis you need to do it. Then impact assessments you need to do it. Interpretation you need to do it. So in order to do the life cycle analysis, there are tools are available. Something like what we use for an artificial neural network for the optimization of process, for the impact assessment or life cycle thinking also. There are some tools are available. Cyber Pro, different softwares are available. You can able to use that. So different types of the models I can say. Cradle to grade, cradle to gate, cradle to cradle, gate to gate, well to be. These are the different way I can say method of I can say designing the model. The ultimately among the 5 things we are proposing, this is very, very important. Cradle to cradle. Right? The person born with the animal or human born in the environment, right? Again, it goes back to the environment. That's called circular economy. That's called cradle to cradle. மனுஷன் பிறக்கிறான் மறுபடியும் இறக்குறான் மண்ணில் தான் பிறக்கிறான் மண்ணில் இறக்குறான். That's called cradle to cradle. So cradle to grave, maybe you can say you are giving some input in the form of raw material extraction, manufacturing, transportation, usage, retail, and waste disposal. So you are not, I can say, bring it back. Only I can say we are aiming for. Suppose you are want to produce some chairs or something, right? You are going to consume the material. So in order to use that material, there are some processes already involved. Right, material processing. So the steels are manufactured. I can say different steels are manufactured through the, I can say, steel manufacturing industry through. I can say take it to the furnace, you take it to iron ore, you are extracting. So there are a lot of processes are happening. You need to bring that also. The raw material collection, you are going to use some kind of, I can say the JCB or the human source, right? Everything you need to take out for extracting the raw material, bringing that from the particular mines to the industry. Also, you need a lot of transportation. It emits CO2, right? Cost you are going to pay for it. Everything need to, I can say, use it for raw material. There are several, I can say, in terms of the cost, social as well as the environmental perspective. That is for extracting the raw material. Similarly, from the raw material extraction to the manufacturing and transportation also, you need to consider all three. Then usage and retail and waste, how the waste is going to be disposed out. Because you are emitting, because the steel industry, lot of emissions are coming out in the form of heat or in the form of emissions, right? So you are going to burn the, I can say, coal or maybe burning the natural gas or I can say liquid fuel to melt the iron ore to get the, I can say, the liquid form of the steel which can be taken for, I can say, different applications. So there are 5 steps we are following: cradle to grave, cradle to gate. That means you produce it and deliver it. That's all. The industry, you are going to consume the material. You are going to produce something. Suppose you are going to produce a TV, right? So you are the job of the company, or you can say automotive sector. They are going to produce the automobile, 4-wheeler or 3-wheeler or maybe the heavy vehicles. Or the duty of the industry is to produce it. It will be handed over to the customer. So that has been cradle to gate. Cradle to cradle means then the same industry will be collecting all the waste material. It is going to be taken into the reuse. It's called cradle to cradle. Gate to gate means the industry is selling, someone is going to collect it. For everything, for all the 5 things, right? You need to think about the 3 steps. Okay, economic, social, and environmental perspective. So different life cycle models are there. Cradle to the grave. So raw material extraction, lot of inputs you are taking, lot of outputs also coming out in the form of money, in the form of emissions, in the form of electricity, everything. Input also you are going to consume some kind of either against the heat or power. Similarly, here also you are going to consume. You are going to, I can say, the output is going to be the product or heat or the emissions. So there are the different steps. To start from cradle to grave, need to, I can say, from the raw material extraction to the material manufacture, then product manufacture, then use stage, then the end of life. So you are going to come across the different steps to attain the final to the grave. So in that, so much of inputs are involved, so much of outputs are involved. You take all the inputs and outputs accordingly. Then if you give it to the I can say life cycle model, you will get the proper outcome. The goal and scope of a life cycle assessment: define the functional unit, define a system, define limit carbon analysis. So life cycle inventory analysis is essentially the data collection of our LCA. It looks at the environmental inputs and outputs of our product and service. Suppose we want to do the analysis for a labor goods, I can say, process. We are having, I can say, several data are available. No need to, I can say, run a Haber-Bosch reactor to get the data. There are millions of applications are available in Haber-Bosch process, right? So you can collect the whatever the inputs are necessary. There are papers are available. You can collect the data, or you can send it to the industry, get the data. So accordingly, you design the the life cycle system. Okay. So what could be these inputs and outputs? Raw materials and resources, different types of energy, water. So these are all data you can easily get in from the industry. They're already running with the conventional method of producing ammonia. If this you can able to, I can say, use it. Some data are available, maybe with some standards are available. You approach the industry, or you can approach the suppliers. Some means you need to get the data, or you can able to, suppose you have a small reactor of, I can say, 100 kg or something. You can run the reactor, you can get the data also. Life cycle incidence and flow model, raw material, right? Raw material and processing. There are different steps. You can see here, raw material goes to the final product ultimately. So different raw materials are involved for different processing. Finally, you will be getting the, I can say, product, energy, or I can say, then the waste will be coming out. Life cycle impact assessments. The common impact categories are human toxicity, global warming potential. So the replacement of the amber bush. Now among the different assessment method, we are focusing on this category, global warming potential, GWP. So how to eliminate the carbon dioxide completely, because to produce 1 ton of ammonia, they are saying that is about, I can say, 100 tons of CO2 will be coming up 100 times. So this is the major among the your idea, which is going to be predominant in focusing. Yeah, carbon dioxide emissions are, I can say, very high. So we are focusing on among the different I can say inputs. This is the most important one. Then ecotoxicity, acidification, eutrophication. All the gases are transposed into CO2 equivalents, whatever may be there, whether it is NOx emissions or SOx emissions or any other forms of emission, you have to equivalent, you have to convert into CO2 equivalent. Normally, I can say even some of the gases are not going to be converted into, I can say, hydrogen in maybe in the steam methane reforming. Then methane also going to be comes out in the reactor. Maybe sometimes leakage also happens. So every I can say constituent you are going to later to the CO2 for doing the global warming potential study. Category, what else can look into this? Environmental cost indicator, I can say, global warming potential, depletion potential of the stratospheric ozone layer, acidification potential of land and water, eutrophication potential, formation potential of tropospheric ozone photochemical oxidants, abiotic depletion potential for non-fossil resources, human toxicity potential, freshwater acuity ecotoxicity potential, marine acuity ecotoxicity potential, terrestrial ecotoxicity potential. So several parameters need to taken into account for doing the, I can say, life cycle analysis. Interpretation of life cycle assessment should include identifying the significant issues based on our life cycle LCI and LCA, evaluating the study itself, how complete it is, if it is done sensitively and consistently. Finally, you need to conclude limitations and recommendations. The conclusion drawn from life cycle analysis is how high are the emissions of the product or service, how does it compare to other products in our portfolio, what are the biggest leverages to reduce the impact of our product, can we be more efficient in manufacturing. The ultimate aim is you are going to provide the, I can say, most efficient method of producing the product if you are able to do the life cycle analysis. So that some inputs are you need to take it for the analysis. If you want to ship the, I can say, ocean shipping, you need to take energy, metric tons. These are all the values are available. Similarly, the carbon footprints are available for different applications, right? Family car, hybrid gasoline, right? Energy in terms of, I can say, megajoule per ton, I can say, megajoule per metric ton, respect to the kilometer also given. So all the data you are able to get. So data are available. You can use it for your analysis. Because we don't know about your manufacturing industry or your process, what are all the factors you are going to really involve in. So there are several factors are available, data are available. You can pick up the relevant data for the analysis. Okay, so in case of, I can say, Hammer by using nuclear energy for producing the, I can say, ammonia. So this is the one way of the, I can say, you can design the system. You are going to use a uranium. So uranium extraction, lot of energies are involved, lot of emissions are involved, lot of peoples are involved. Then you are going to take the uranium into nuclear power plant, you are going to produce the electricity. There are so much of inputs are coming, so much of outputs also available. Not only producing electricity, and also you are producing toxic, I can say, emissions, or maybe the nuclear waste going to be very hazardous. That is all you take it to analysis. The electricity, you can take it from the, I can say, it comes from the nuclear reactor, a pressurized water reactor or something from the case of nuclear energy. That electricity can be used for electrolysis. So in that case, in the electrolysis, the inputs are electricity, water, then nuclear heat. So whatever maybe the parameters are entering from the input, outputs are, I can say, oxygen, hydrogen, along with the heat also comes out. So suppose you are using, I can say, other than the water, some other hydrocarbon, we are going to use it in the, I can say, the electrolysis process or something, we can say, or the reforming process from the electrochemical method. So other products also will come. So here we are going to using water, so you will get hydrogen and oxygen. The other things also taken into account in terms of, I can say, other than that, heat will also comes up. Water also maybe sometimes will be, I can say, the leakage is going to happen also in the reactor or through the transportation, right? And whatever will the cost involved for purifying the water from the water where it's consumed. It's going to be something like a distilled water, right? So distilled water is not available in the nature. You need to produce the distilled water. What are the energy consumed for producing the distilled water from the normal, I can say, potable water? So that also you need to take into account. Okay. Ultimately, here the hydrogen comes out. Electricity also you need for the producing the ammonia in the Haber-Bosch reactor to produce the, I can say, the pressure and temperature. Then ammonia synthesis is happening. So ammonia is going to be comes out during the reaction also. There is a lot of energies are involved, lot of input materials also involved, lot of emissions also will comes out. So that also you need to take out into the account. Then the output, not only ammonia is coming out, so other than the unreacted species also comes out. Maybe if you recycle it, well and good. Something if you are giving to the surrounding also, that also you can take it into the account. Then you are going to store it. Storage also, you need a low temperature, the storage device to store it in the form of liquid. So that also you need to take it to for the life cycle analysis. Then you are going to provide some kind of energy to separate out oxygen, nitrogen by using the permeable membrane. So inputs are energy and air, outputs are oxygen and nitrogen. Along with that, I can say some amount of heat also will come out because you are going to send high pressurized air. So other forms of energy also will come out. That also you take into account. Okay. The simple one. This is the simple one. But don't assume that this is the only simplest I can say. For each understanding, we prepare the flowchart like that. Suppose we are using biomass as a material, municipal solid waste as a material, or hydro is the energy as a material for producing the power. Accordingly, right? If suppose we are talking about biomass, the energy you are absorbing from the solar to produce the biomass, then for harvesting, transportation, then bring the biomass into the required size. All those things you take into account. Then during that transportation, some biomass will be, I can say, you are going to lose somewhere. So everything you will take into account for producing the power. Biomass you take it into the either the thermal power plant or you take it to the gasifier or pyrolyzer, way in which you can able to produce other products, then you can able to produce the power. Okay. So ultimately here the input power comes out. First one is nuclear, next one is the from the biomass or municipal or hydro. So whatever when the inputs are entering in the form of energy in terms of the mass or the output also, I can say in terms of the mass, in terms of the energy, and also in terms of emissions. Other things are remains. Okay. So if you this is a continuation of the previous one only. If you are consuming energy from the hydropower, so need to take out the different inputs and in terms of water flow or in terms of the conditions in which you are going to provide that one, that you need to take into account for producing the electricity. The other things are used. So you can also, this diagram talks about, you can combine the two forms of energy also. One is hydropower here for producing the, I can say, hydrogen and combination of, I can say, hydrogen into ammonia. There are two different sources they can try here. One is the hydropower, another one is also nuclear also. If you have electricity, you can use any type. That is the thing. You want to bring it here. Then you are bringing the different, I can say, way of using the power, energy efficiency perspective. Energy efficiency high for hydropower. Nuclear is 23.8. Biomass based electronics is 15.4. The 19.7 the municipal waste. So among all the methods, if you are going for biomass and municipal, the energy efficiency conversion is low compared with nuclear and hydropower. Because the loss is going to be less for hydropower as well as the nuclear power, whereas the loss is going to be, I can say about 85% conversion. 85% is lost here, whereas for municipal service about around, I can say 89% is going to be waste. So need to find out the way in which that can be improved by doing some kind of analysis. So exchange efficiency, how much the work potential for the given heat input, how much the work you can able to extract it to the maximum level by keeping the surrounding into account also. So you can see hydropower, the work potential is going to be very high. Suppose we are producing, I can say 100 as the input, the output is 46.4. So the conversion is about 46.4% from the input. Then the nuclear is about 20.4 and biomass is about 15.5 and I can say ammonia is 10.5. Assume that if you are adding 1 kg biomass, then the conversion is going to be among the maybe I can say 100,000 grams. You can say the conversion is only here 15 grams. Okay. So here municipal one is only 10 grams. So here because the calorific value is very low and no, that is the reason why the energy efficiency are, I can say, very low. So we need to use some kind of method in which improvements are possible because during the process a lot of wastage comes out. You can again send back to the system. You can able to improve the efficiency. Other than providing the energy in the form of work, mechanical energy or work, in the form of heat, in the form of electricity, you can also provide energy in the form of heat to boost the energy efficiency, which can able to increase the ammonia yield, I can say, to 5. Okay, exchange efficiency of various ammonia production methods we have proposed, right? So ammonia from municipal, I can say, then ammonia from hydro, ammonia from nuclear, ammonia from biomass. So you can see here, among these, the major emissions, CO2 emissions, among the 4 methods we are proposing here, this is going to be maximum for from the biomass electrolysis. Next one is the nuclear. Then the hydro is going to be having the minimum CO2 emissions. Then you can say from hydropower, this is the, what is this? Municipal solid waste. So this is another advantage you can see here. By going for municipal solid waste, we can able to see that the minimum CO2 emissions are coming out. This is the positive sign. That means we can able to use the municipal solid waste for producing the electricity or heat. The amount of CO2 comes out is going to be very low. Because the municipal solid waste, why the efficiency, I can say the CO2 emissions are very low means most of the constituents present in the municipal solid waste is less carbon in nature. Okay. So this is the general layout of the life cycle analysis. So need to, I can say, find out some method in which you are going to do the life cycle analysis. You can say inwardly, we can say ISO 14004 2006. This is the standard available. In order to do any kind of analysis, you need to follow the standard. It is proposed in 2006 for the cradle to design the cradle to gate and gate to grave and cradle to grave. You can say these are all the standard available for collecting the data to do the analysis, right? So ultimately, you need to collect the data. You need to use the database, and you must have the maximum number of data to get the I can say good output coming out from the life cycle analysis. So there are databases. You need to create a database. Need to feed the data into the software tools. There are tools are available. Eco-Invent, Gabby, right? Cyma Pro, Gabby, and Open. So in order to use the, I can say, store the data as well as for do the analysis, there are some softwares are available. So we are in NIT also, we are trying to procure this one, which can, because life cycle is very important. Most of the journal papers now they are considering only if some kind of new things are happening available in the literature, right? In the paper. So in that case, if any of your work contributes. For example, if you are doing some kind of catalyst process or new catalyst, right? So there also you can do the LCA. Okay. So the Gabi, CyberPro, and Open LCA, the softwares are available. Open LCA, you cannot have all the features, but they are providing, I can say, the free software that is specifically for the students. But if you want to do some kind of project, undergraduate or postgraduate project, you can make use of the Open LCA by providing your I can say, your informations. You can able to use it. But when you go for, I can say, research level, PhD level or industry level research to do the life cycle inventory or life cycle analysis, then you need to procure any one of the software to do the analysis. So this is the general to identify the different I can say category of how we are going to produce the ammonia from different various sectors. You can see here. So brown ammonia, blue ammonia. If you, what do you want? You want a green ammonia or brown ammonia or blue ammonia or grey ammonia or Turkish ammonia or pink ammonia, right? Accordingly, there are several systems to be added for LC analysis. Okay. But if you talk about the brown ammonia, I can say the method what you are proposing is the gasification, coal gasification. Then coal is the raw material. Then the product is you are going to produce some kind of electricity, but CO2 will be coming out. So right, that's called brown ammonia. Right. So the hydrogen can be comes out from the gasification. It's called brown hydrogen. That can be taken for the taken into the vapor post to produce the ammonia. But we are not calling it green ammonia, it's brown ammonia. When you are using coal as a fuel in the gasification method is a thermochemical conversion system, then the ammonia generation, hydrogen generation is called brown. Then we can go for blue ammonia and the same system, coal as a fuel, gasification is the thermochemical conversion system. But if you are not recovering CO2, it's called blue, I can say brown hydrogen and brown ammonia. If you are recovering by using a carbon capturing system, it's called blue hydrogen. But the raw material or the fuel is coal. Then we can say, I can say by using a natural gas. So coal, if you are going for steam methane reforming, from the methane, natural gas, you are producing the ammonia. That's called grey ammonia or blue hydrogen or grey ammonia. Okay, the raw material, the fuel, the raw material source or the fuel is not coal, it is methane. Okay, so natural gas. Then the natural gas will be used for cracking or pyrolysis or chemical looping. Then the way of the product comes out from the reactor is called Turkish hydrogen. Okay, the ammonia is called Turkish ammonia. Okay, so the natural gas is taken for SMR. It's called blue hydrogen or grey ammonia. The natural gas, the methane, taken for pyrolysis reactor or the chemical looping or cracking system, where the reactor is producing hydrogen is called Turkish hydrogen or the ammonia. The ammonia comes out from the Turkish hydrogen is called Turkish. Then if you are using energy from the nuclear power plant to produce the hydrogen, it's called pink hydrogen. Okay. So here we have various ways of producing the hydrogen, various ways of producing ammonia. If you are using coal, it's called brown. If you are using same fuel with the CCS, carbon capturing system, it's called blue hydrogen. If you are using natural gas with carbon capturing system, it's called blue hydrogen and grey ammonia. If you are using same natural gas with a different reactor system, the hydrogen comes out is called Turkish hydrogen and Turkish, the ammonia coming out is Turkish ammonia. Then the electrolysis, you need electricity to dissociate water into hydrogen. The hydrogen comes out from the reactor by consuming the nuclear energy. The electricity comes from nuclear power plant is called pink hydrogen. Then the hammer boats who are producing ammonia is called pink ammonia. This we already studied. The ammonia comes out in the form of, I can say, renewable energy source. For electrolysis, we are using solar, wind, renewable based energy to produce the hydrogen is called green hydrogen. Then the ammonia, you can go for either hammer boats or I can say electrochemical method way of producing ammonia. You can, it's called green ammonia. Okay. So there are different inputs are entering. For electrolysis, you are adding water. For I can say for the power plant, you are providing solar and wind. So there are inputs. Then for providing ammonia, so hydrogen comes out from all the methods. You need to provide the nitrogen. So from the gas separation unit, you are providing nitrogen to the brown hydrogen, blue hydrogen. turquoise hydrogen, pink hydrogen, and green hydrogen. The reaction is happening in the Haber-Bosch reactor or in the electrochemical method. You are going to produce the ammonia. Further, you need nitrogen. Nitrogen will be provided from the, I can say, air separation unit. So in order to produce the, in order to provide the energy for the air separation unit or the for electrolysis or to transport the water, you are also consuming the energy from the solar, wind, hydro, or sometimes you can take it from the, I can say, the general power plant also. Maybe thermal power plant, similar to by using a solar energy as a material, you can produce solar energy. This is very important slide. It talks about the different ammonia. So the ammonia comes out and the different, I can say, shading they are providing. It purely depends on the raw material and also their and the raw material and way of the hydrogen comes out. So this is the assignment. You can try. You can move this one. This is sharing or video. That also assignment. Please try compare and contrast the life cycle assessment of the conventional ammonia synthesis process with the advanced green ammonia synthesis process. Highlight the environmental, economic, and energy efficiency implication of each process and propose strategies to further enhance the sustainability of green ammonia production. Draw the detailed flow diagram. I didn't want that value. So need to, I can say, come up with now you know the how the Haber-Bosch systems are now working from the conventional hydrogen to the Haber-Bosch and also the green way of producing ammonia from the electrolysis to the ammonia in either Haber-Bosch or I can say electrochemical method. You can try to draw the flow diagram. So which one you are going to use it? Suppose you have an idea about going for biomass, then you can come up with a new layout of I can say producing the hydrogen and ammonia. Then what are the parameters are really involved for life cycle analysis? You draw the flow diagram. That is tutorial. Today's tutorial. Thank you. You can distribute the answer script. So you can keep this one in mind. You can keep this one in mind, right? You can try to draw that flow chart. Suppose you are going to do the life cycle analysis, right? So you need to find out some parameters. What are the input parameters? What are the output parameters? So you need data also. I'm not expecting any data from you. I want how to start the life cycle analysis. No diagram. Just these are all things are why we are going to bring this one. This is why we need to provide electricity, we need to provide the heat, we need to provide air, and we need to separate out the nitrogen. Some systems are necessary. So unless otherwise you can write the flow chart, including the components are involved for the process, you cannot come to the results. Maybe the LCA process needs 1,000 components, but at least you come across with at least 100 components. You can get some results. The results may not be acceptable. Then you can go to the reverse one. So what are things still they are expecting to do the life cycle analysis? Please try. Or you can take this one, any one process among these, you take. I want to produce the ammonia from the coal. One person can do it. One person can do. I want to bring CCS. So what may be the system diagram? This is only simplified diagram, right? So you need to bring the mass flow, energy flow, and emissions perspective also need to bring it. Social, economic, as well as the social, environmental, and economic. You can bring it. So don't need to take or you take any one. So suppose you must have at least one conventional and one renewable. Right? I think if you have any queries, further more discussion, I think Uday Kumar, you can spend time on it. You take one thing and you can explain to them. Maybe the conventional way of carbon, I can say, from the coal, CCS, how to go for LCA. You can go ahead.
For example, if you take conventional route means Haber-Bosch process, so that Haber-Bosch before entering into the LCA, we have to think what are all the input, what are all the output, what are all the emissions. These three are major things. We will see that in field also, what are all the input. So first, if you think about, if you take one system, for example, now I want to generate hydrogen. From after hydrogen generation only we can go with the Habermas. So first I take the process of producing hydrogen. Any method you can use, steam reforming you may use, electrolysis you may use, or else you may take that from other way of extraction like gasification, plasma treatment, anywhere you can extract hydrogen. So first you have to think what are the input for the process. So now we can take a familiar process. Simply we may take means electrolysis we may take. If you take electrolysis means what all the things are coming as input. That input may be a water source, maybe electrical energy, or maybe air. We are taking air from ambient, or maybe nitrogen. Nitrogen means that also we are taking from ambient means you have to consider that you are taking from nitrogen cylinder, a pure oxygen. So any source get into the process. If you take manufacturing process means the material like metals, the catalyst used means then how catalyst is entering. Before that, Saab discussed gradual to gradual approach. So gradual to gradual means where we are starting, we have to end with the same. Gradual to gradual is not possible directly. Gradual to gradual can be achieved by through gate to gate approach. Gate to gate means that is like one process. If you take refrigeration system means we are considering refrigerating system as a flow process. Only condenser we consider as a flow process. So take his input, energy in, energy out. We evaluate steady flow energy equation. Similarly, you have to evaluate what are all the materials in, material out. Emissions. Other than material, other than energy, emission level you have to consider such a board actually. One system we can expect.
The drawing schematic and we can expect. They are aware of one thing, then they can take it for the next system.
Now we can list what are all the input, what are all the output. For electrolysis or electrolysis process, first major input is water, electricity. Then any other input for electrolysis?
Salt.
Electrolyte, electrode. Similarly, not only this. For example, you are mounting that in you are keeping electrolyzer in some place. So in that place, you are utilizing air conditioner, or you are utilizing fan, you are utilizing light. So that also you have to consider. You could not predict everything. Then you can take that as a miscellaneous or other energy resources other than listed thing. Like you can take. Then first you have to draw like that. Then you have to segregate what are all the materials in, what are all the energy in, then what are all the emissions. So like you have to take. So from the electrolyzer, what are all the things you will get as an output. Ultimately, we are doing that for hydrogen, and then other than hydrogen also coming from electrolysis. So what are all the things that may be gases. So many gases are possible. Then what about other output? Similarly, you have to think small component. Like you can take your own house TV. What are the input? What are the output? You're taking electricity from grid. So before entering to the grid, that grid electricity, for example, that is consuming 1 kilowatt hour. Like I'm assuming. So 1 kilowatt hour I'm collecting from grid means that contains CO2 equivalents. The same 1 kilowatt hour I collected from my own house solar PV system. Then the CO2 equivalent is not similar to this. Grid electricity have one CO2 equivalent. Our PV system have another CO2 equivalent. Similarly, my PV system is apart from away from 1 kilometer means I'm transporting from there to here. So that transportation, energy transmission from there to here, lots of losses are there. We have to consider that also. So here I need 1 kilowatt hour means there I have to produce 1.2 or 1.3 kilowatt. So I have to consider that CO2 equal. Similarly, this is for emission aspect. From here to here, how much CO2 is coming out. So that only displayed here. 3 kg CO2 equivalent is coming from this 3 kg per kg. 3 kg CO2 equivalent per kg ammonia products. Similarly, you have to calculate. This is only global warming potential. Life cycle assessment not only having global warming potential. As are already listed in the PPT, so many things are acidification, human toxicity, everything is there. So what you need, based on that you can take. But you only consider the global warming potential, then that are not sufficient. If you consider 2 or 3 parameter combined, then you have to take it. So here water I am taking from borewell means here it contains CO2 equivalent. Similarly, first you have to list out the input and output. Then after list out the input output, so here how much global warming potential. Acidification means that we are equated with the SO2 equals. Similar to global warming potential, acidification potential, that SO2 equivalent, like we can equate it. In the previous slide also, I hope you noticed 1 kg CO2 equivalent for 1 kg methane is equal to 25 kg CO2 equivalent. 1 kg NO2 is equal to 240 something, 35 to 40 kg CO2 equivalent. So similarly, you have to calculate all these things and you have to compare. Now, here you obtained some quantity of CO2 equivalent, global warming potential assumption side. Then this side you are getting hydrogen. That is output. And then remaining thing, what all the things are coming out, that may be useful for next process. If you take pyrolysis process, means then the pyrolysis oil will be useful to next. So that oil carries, that 1 liter oil carries this much CO2 equal. For producing, for example, here I am producing 1 kg hydrogen means that hydrogen carries sum of all these CO2 equivalents. So 1 kg hydrogen production needs this much quantity of CO2 equivalent. Here 2 kg equivalent CO2 equivalent. Here 2 kg equivalent. Like you can add and then 10 kg equivalent of CO2 for producing 1 kg hydrogen. Like you have to derive. This is for global warming. Similarly, energy aspect you have to think. For producing 1 kilowatt hour electricity, how much energy is needed as input? For producing 1 liter water, you may take it from well, you may collect it from river, you may take it from outside source. So you have to consider, if you collect from through lorry means you have to consider lorry. 1 lorry water I am buying, so that lorry charge, that lorry emitting CO2. Emission aspect, you have to take that transportation charge also. You are collecting, I already said, your grid is away from your home, and then the losses also you have to consider. By going deep, it will give good output. By assuming or by simply taking or simply assuming or simply ignoring the deep component, then our analysis report will be rough. It need not to be valid. So it should be valid means you have to go into deep and you have to consider each nook and corner. Every point you have to consider. I hope you got idea. Now you can draw your own system and you can write what are the input and output. Then that input and output you can divide that into 2. For this class you may consider global warming potential only. Then energy, global warming potential. How much energy input, how much energy output, how much global warming, how much emission you did by that process. Similarly, you have to calculate. You draw, and if you have any doubt, you can ask. I will give my, if I know, we can discuss. Any one process. Don't take bulk, because bulk analysis is very difficult. You have to consider very small portion, gate to gate, then you have to combine all gate to gate aspect, then you have to combine into gate to gradle to grade. So you have to build like that.
Do it for any one process, one system, completely by taking into account. Then for any system, you can able to do it.
Yeah, this category is alone.
You can do it.
If you are familiar with the electrolysis, then that alone you can take. If you are good in plasma catalysis like plasma, that process alone you have to take. You have to analyze that alone separately. Then only you can able to compile.
But maybe the area you are familiar, that alone you first work on it. Suppose we are working on a fire analysis, work on fire analysis area.
Because then only you can able to
It's called gate to
feel
gate.
the input and output.
It's called gate to gate. So we first study one completely. You take it to the next system. Well, by doing this analysis, you can able to understand that. So there are so many components are involved in getting the product. In terms of social, in terms of economic, in terms of environmental perspective, so many things are involved. That and now you need to add into your product. People are saying that you are using this particular system and producing so much of CO2. Unless otherwise you cannot have complete study, then prove that you're not producing any CO2 emissions more than what is given by the government. This study will help you for it. Even for fixing the product cost also, this is very important. Because you want to design a new product and you are going to fabricate a new product. If you are able to do this study, LCA study, then by bringing all the three components into account, manpower and environmental perspective and the economic perspective, then you will not get any against say. Suppose you are designing a product 100 rupees by completing all the research, LCA analysis, then you may not get any against say loss in the particular product. Some products are really successful, some products are now they are putting some value and getting after some time they are going to get companies at loss, right? Because they didn't do the proper analysis. The life cycle analysis will helpful not only for against getting a good product and a good way of producing the product also. You can able to get it. So you can think about that. Maybe today or tomorrow, or maybe sometime you may come up with the real way of doing the analysis. Then somebody is working in industry, you can able to save where I can able to save the particular implement this concept in terms of economical perspective, can say environmental perspective and social perspective. I can bring this some kind of product which is going to be acceptable by everyone. So with this, I am completing the 4-note first session. So I am completing the 4-note first session, and we will break for I can say tea. We will be meeting in our laboratory for a demonstration. Then for the next tutorial, then we will break for lunch after that. Total 15 days. So 15 days. All of you assemble in thermal laboratory within 10 minutes of time.